This is Jack Jackson. In this video, we're going to be talking about power functions and their derivatives. Okay, so we're going to get a power function rule, or just a power rule for short. So it turns out that a power function, of course, is a function that looks like this. F of x equals x to the n, where n is a constant and x is a variable. So it's a variable base and a constant power. This is a real basic, most basic power function. We can transform this by, putting in a coefficient or adding something to it. But just a basic power function is a real simple function in one sense. It's a one-step thing. You take a variable base and you always raise it to the same power each time, like y equals x squared, y equals x cubed, y equals x to the 3/4, etc. Those are power functions. And it turns out there's a really simple rule that it turns out to be, and it's the derivative of x to the n power is n times x to the n minus 1 power. Be sure that you're only applying this when you have a variable base and a constant exponent. Now I have this GeoGebra activity here that we can pull up, and here it allows us to experiment with this. For example, I can change to say a good old easy one like y equals x squared, and the derivative is 2x to the first power, and so that's what that looks like. But I can also change the other powers here. I'm going to think of these powers as fractions, p over q, where we have rational powers. You could also have an irrational power as well, so we'll talk about that briefly as we go along here. So the first thing that we might want to do is to review what are some basic characteristics of the graphs of these different power functions. We studied this back in our first unit, which we reviewed from pre-calculus. So hopefully you studied these in pre-calculus. If not, you could go to my videos in my algebra playlist that talk about power functions in more detail, and then you can also go to the summary video that I did back in the first unit of the first playlist of calculus. But let's just real quickly review some of these things. So for basic power functions, it's a positive number to any power is always positive, so they always include points in the first quadrant but never any in the fourth. 1 to any power is 1, so the point 1, 1 is in common for all these functions. 0 to any positive power is 0, so 0 is a common point for all the positive powers, but if you have a negative or 0 power, 0 to that power is undefined. To the right of x equals 1, the higher the power, the higher the graph, and between 0 and 1, the order is reversed. The higher the power, the lower the graph. So if you're looking at the first quadrant here, which they all have, they all go through this point 1, 1. All the ones with positive powers, which would be these, all go through the point 0, 0. The ones with negative powers and 0 power do not go through that point. 0 to the x to the 0 power is just a horizontal line here with a hole in the graph here at 0, 1. If it's a negative power, it has vertical and horizontal asymptotes here of the y and x axes respectively, and they're decreasing concave up there. And so they're down here. If it's n equals 1 for the power, that's a horizontal line. In between 0 and 1 are increasing concave down, and positive, and n equals 1 is a special one for the power. That's just y equals x to the first power, and I've got it mislabeled. It's this one right here. Let me fix that. Now we have that. That's the one that's a straight line. That's this one right here, going through things such as 2, 2, and 2.5, 2.5, and 3, 3 there. And then the ones that are increasing concave up are these right here, which are powers bigger than 1. And the bigger power is going to be higher, so I don't remember what these powers are, but these are going to be, like one of these might be down here, might be, let's see, negative 1 power is this one right here, and so maybe negative 2 power might be, I think maybe this one right here. And this would be, so notice that's the lower power is lower down here. Works its way up to higher, but still negative powers as you go up here. Then a power 0, then this one might be, let's see, one of these is a half power, I bet. Let's see. It would go through 4, 2. No, I don't have a half power. I have some other powers. So this might be less than a half. That's a little bit bigger than a half. A little bit bigger still. Then it gets up to 1. Then it gets up to, see, somewhere in here we probably have maybe power 2 or 3 or 4 or 5. I don't know what these powers are, but they get bigger as we go up this way. Notice when you go, they cross over each other here at 1, 1, and between 0 and 1, they're exactly backwards. The negative powers are the high ones here, with the lowest one here being the highest one here, and the next to the lowest one here being the next to the highest one here, and so forth. And the lowest one here is the highest one over on this side. So they reverse order. So here the higher powers are down at the bottom, the lower powers are up above here. So they all have a first quadrant portion of the graph. When n is greater than 1, it goes through 0, 0, and 1, 1. It's increasing concave up in the first quadrant. If n equals 1, then, of course, that's just y equals x. That goes through 0, 0, and 1, 1 in a straight line, linear, increasing. Between 0 and 1 for the power, x to the n is increasing but concave down, going through 0, 0, and 1, 1. If n equals 0, we got a horizontal line at y equals 1, except it has a hole in the graph at 0, 1. So in the first quadrant, that's constant and, of course, linear, straight. And then if n is negative, n is less than 0, in the first quadrant, we've got a decreasing concave up with asymptotes of the x and y axes. And it still goes through the point 1, 1 right there. Now, it's useful to think of this power as being a fraction power, which is why over here in the app I have it set up that way where we can think of that as a fraction. If we think of this as a reduced fraction, then it turns out that we can see some things about what happens when x is negative. We know when x is positive, y is positive, so that's first quadrant, never fourth. But what happens after that? So let's take a look. Let's start down here at the bottom. If you can make it into a fraction where it's reduced, that's the greatest common divisor of the numerator and denominator, p and q are 1, so it's a reduced fraction. If they're both odd numbers, then you've got a negative power, negative number to the p power is negative to an odd is negative, and you take an odd root of a negative, you get a negative. So that says negative input gives you negative output. That turns out to be quadrants 1 and 3, and it turns out to have a rotational symmetry about the origin of a half circle, pi radians, 180 degree symmetry about the origin. If the power is an even over an odd, then that power function will end up being in quadrants 1 and 2 and have y-axis symmetry. And that's going to happen because if you take a negative number to an even power that becomes positive, then you take an odd root of a positive, you get a positive. So negative input gives you positive output, that's quadrant 2. But if it's an odd over even, then when you have a negative to an odd power, that becomes a negative, and you try to take an even root of a negative, you don't get a real number. So for our purposes graphing here, you don't get anything for an output when you have a negative input. So that means there is no quadrant 2 or 3 or 4. You only get quadrant 1. And if n is irrational, that's also going to be quadrant 1 only. So n to the pi power, for example, would be only quadrant 1, and then there's no symmetry there. So if you put these pieces together here about the symmetry and these pieces together about the size, we get the following summary for basic shapes. If n is greater than 1, the graph is in quadrant 1, increasing and concave up, which you can see here, here, and here. And that's going to happen if it's quadrant 1, only no symmetry, that would be odd over even or irrational. That looks like this. Even over odd, rational power, looks like quadrants 1 and 2. So the second quadrant's a mirror image of the first. And if it's odd over odd, the third quadrant's a rotated image of the first one. n equals 1 is one specific one, so it doesn't fall in these categories. It's just a straight line, y equals x, and sure enough, it has origin symmetry. If n is between 0 and 1, we're talking about increasing concave down in the first quadrant, which all these have. Again, this one on this column is irrational or odd over even, so it's quadrant 1 only. The middle one is even over odd for the power, so that's quadrant 1 and 2, y-axis symmetry. Odd over odd is quadrants 1 and 3. It looks like this. N equals 0 is a very specific one, y equals x to the 0, which is a horizontal line, y equals 1, but with a hole in the graph at 0, 1. And if you have a negative power, the first quadrant is all decreasing concave up with asymptotes of the x and y axes. Again, if you have a power that's odd over even or irrational, you only get the quadrant 1. If it's even over odd, you get 1 and 2, and they're mirror images. Reflective symmetry about the y-axis. And then here we have a rotational symmetry about the origin. So the third quadrant is a rotated image of the first quadrant when we have odd over odd for the power. And so that summarizes what all the different ones look like. So that's a very quick summary about that. If you want a slower examination of that, you should go back over the results that I had earlier, either in the Unit 1 or especially go back all the way back to the algebra videos over this.